All right, welcome back to Unit 7. In this unit, we're going to talk briefly about vectors. We're really just going to be using some skills that we've used in our last few units, specifically on trigonometry. And yeah, actually, that should probably cover most of it. Um, Everything we're going to be doing is ultimately going to be related to right-angled triangles. Even the things that don't look like they're right-angled triangles, we're going to kind of deal with them as if they are. And it's going to be a fairly short unit. We're only going to be spending 3 lessons on this. The first lesson is going to kind of go over some basics of what vectors are. The second lesson is going to be about dealing with them. And then the third lesson is going to be dealing with some slightly more complicated problems, but it's really just the easy problems put together into a couple in one. Anyway, to start off with, let's talk about what scalars and vectors are. Many students haven't heard these words, or if they have heard them, they're not sure what they are, unless, of course, you've taken physics, in which case you might be a little bit more familiar with vectors. Scalars are just fancy names for numbers that you've been using for your entire life. So lots of things are scalar numbers, and it's any quantity that has a magnitude, but not a direction. So for instance, age, 18 years, that is a scalar quantity. It's a number that has no direction to it. I should point out that scalars can be positive or negative, but they don't actually have a direction associated with them. So other things like length of 3.7 meters or a temperature of 22 degrees Celsius, basically all these things down here as examples would be things to be looking at for examples of scalars. Vectors, which is what we're getting into kind of, again, for most of you, this will be new, but they're just magnitudes that also have directions associated with them. Now, we can put any direction we want on these, but we're going to pretty much, for our examples, stay with like the cardinal directions of north, east, south, and west, because it's just easier to do most questions this way. But some examples of vectors would be 200 meters to the east would be a good example of a displacement. Velocity, which in English often gets used interchangeably for speed, but is actually something different. A speed tells you how fast you're going. A velocity tells you how fast you're going and in what direction. And in this case, I just put down forward. And in some questions, that's all we have to do to be. It's kind of vague, but given the context of most problems, we'll be able to figure out what that really means. And forces, most people don't know this, but when people talk about their weight is actually a vector quantity. Your weight is a certain amount of force that's pulling you down towards a gravitational body like Earth. If you're talking about your mass actually is a scalar quantity. Mass stays the same no matter where you are, but your weight changes depending on what object you're being drawn to, whether that's Earth or the moon, or if you're in deep space and there's nothing pulling you at all, then we often say you're weightless. So weight actually is a vector quantity measured in newtons. Of course, what we really do is we use scales to measure our weight, and what we're really measuring is our mass, or vice versa. We're actually technically measuring weight. We're seeing how much the scale is compressed by how much we push down on it, but we're reading it off as a mass. We're saying it's in pounds or kilograms, whereas really forces should be measured in newtons. Directions, whenever we use them, are going to be put into square brackets, and you can see that in all the examples that we've done here. We got square brackets on east, square brackets on forward, and square brackets on down. It's just so that we don't confuse it with other notations, since there are lots of things in math that use round brackets. Okay, so vectors essentially are just going to be arrows as far as representing them goes. And often we don't draw them exactly right. Obviously, I can't draw an arrow that's 100 kilometers eastward because I don't have 100 kilometers worth of paper. But even so, we could draw them to scale, and in many cases, it's helpful to try and draw them to scale. But for our purposes, as long as we're somewhat close, that we can use the picture to kind of gather what kind of information we need from it, we're not going to worry too much about it. So for instance, if I look at the two arrows on the paper here, 100 kilometers east and 50 kilometers north. This, of course, is going based on our normal cardinal points of north, east, south, west. And I'm not sure why I drew that because I think it's literally right there above us, north, east, south, and west. And anyway, the actual lengths of these, the northward arrow is not exactly half of the eastward arrow. They're just approximates to kind of show what's going on. I should also point out that I used to do military courses where we teach map and compass use. And a very major misconception, although one that most human beings use, is that on a piece of paper, up is north, down is south, right is east, and left is west. And that's not obviously true, because if I turned around, east and west would switch directions, and that's not how east and west work on Earth. East is one very specific direction, and west is the opposite of it. And likewise, north and south are not up and down. Up and down are vertical directions. North and south are horizontal directions, the same as east and west. They point towards a direction along the horizon, not straight up or straight down. I do not get to the North Pole by getting into a rocket and going straight upwards. Likewise, I don't get to the South Pole by getting into a digging machine and digging straight down. Just a interesting little misconception most human beings have. So again, I've listed some of the standard directions here, up, down, left, right, forwards, and backwards. And those are good depending on the questions that we're doing. Then we do the compass directions, north, east, south, and west. And like I said, I think for our examples, we're going to kind of stay more or less with those just because they're easier to work with. And then we have things like complex directions, which can be actually represented in several different ways. And to be honest with you, it depends on what application you're using to see which type of way that you'll express the directions. So for instance, geologists, engineers, earth sciences, aviation, etc. They all use slightly different notations depending on what their application of this is. We're going to stick with the notation that I'm using here of, well, I'll just zoom in a little here and we'll take a look at these. This first picture, what we do to name our directions is normally we kind of look at the major direction, the direction that most of the arrow is going in. So for this first one here, you'll notice that the arrow is more up than it is in any other direction, or more north than any other direction, but it's a little bit east. And so the way that I would define that is by saying my dominant direction is north, and then I'm going to turn 20 degrees to the east. So dominant direction is north, and then turn 20 degrees to the east. Similarly with the second one, we're going to head west, and then I'm going to turn 35 degrees towards the south. So we say that's west, 35 degrees south. Now I will point out, and we'll see this a little bit more later, you can actually do stuff like, for instance, south, which is not the dominant direction, and then how many degrees is it to the west? And I believe that's going to be 55 degrees since the two have to total 90. So I could actually list this direction as south 55 degrees west. Again, depending on the application you use or what field you're going into, there may be a preference as to which one of those is favored. In this course, I'm going to say that normally we prefer the one that has the most dominant direction first, northeast, south, or west. And the second direction is the minor change in that. Now, some fields will say that they always want the north and south first, and then how much to the east and west you're going, in which case the second form would be the one that they would want, south and then 55 degrees to the west. Truthfully, on our tests and stuff, I don't care which form you use, and in fact, there will be one question that will ask you to do in both forms, and just to make sure that you understand how they're related. But my preference would be dominant direction and then a small angle towards a secondary direction. All right, let's use that to just try a couple of these and make sure we understand them. If you'd like, you could pause the video right now, try these on your own, and then come back and see if you did them correctly. But I'm going to just keep going, assuming you're not pausing the video. So for these vectors, and oh, by the way, you'll notice in this picture it has it. Vectors are often given variables, the same as any other quantity is in math. And they're given a little arrow over top of them to let you know that it is a vector quantity. Now, just because it's a little bit small on the screen, I'm going to try and show you that it doesn't matter how you do your arrow. So some will make it look like this, like, oh, it actually did like a little weird arrow. Some will make it look like it's an actual arrow, but if you want to do it with just one single head, that's fine as well. It's more like a font difference than it is an actual mathematical difference. Anyway, our vector quantity A is going to be 10.0. This one doesn't give us units, so we'll just say that it's unitless. And then we have to put a direction on there in square brackets. And that's going to be mostly to the east, but then 30 degrees to the north. And that's really all there is to defining directions and magnitudes of vectors. For vector B, I'm going to go down a little bit because I have a feeling I'm going to run into each other if I don't. This one has a magnitude of 5.0, and its direction is, now the way that it's drawn, it would be east 53 degrees to the north. Or if you wanted to write it, you could put it as north and then be 37 degrees to the east. So basically this part here would be 37 degrees, again, because the two angles have to add up to 90. For C, that's going to be 12.0 units. And the direction on it is well, sorry, I shouldn't say mostly, but the way that the picture is drawn, it's going to be east 60 degrees south. If we did it where we do the dominant direction, that would be south and then 30 degrees to the east. And finally, the last one, which is actually a little bit more properly drawn, it's 20.0 units, and its direction is dominantly to the west and then 37 degrees to the north. All right. One of the reasons we're going to do most of our examples with north, east, south, and west is because it becomes kind of complicated using the terminology when you're doing things like this vector is, up 20 degrees left. Those are things that are hard to visualize. So we're just going to kind of pretend that we're dealing on a flat piece of paper with north, east, south, and west and do our questions that way. And if in any real application you had to do some other directions, like I said, forward, backwards, up, down, left, right, etc., you're more than welcome to do that. It's the same math. It's just a little bit more complicated to think about. Okay, so a few things about working with vectors. The first is a property that's also true with scalar values, and you've known it for a long time. And that's that if you add two numbers together, two scalars together, the order of addition doesn't matter. 3 plus 5 is the same thing as 5 plus 3. Well, as it turns out with vectors, that is also true. The pictures look a little bit different, but the actual result is the same. So if we say we're going to go north and then east, so A plus B, that's going to give us a resultant vector, which is just a fancy name of saying the vector we get as a result of adding two vectors. That looks like that one. That one is a little bit more east than north because the eastward vector was a little bit longer than the northward vector. But if we switch the order of the vectors and did the east one and then added the shorter north one, we would get the exact same arrow. And you might say, well, aren't these arrows in different places? And the answer is they both basically start at a point here and end at a point up there. This one starts down here and ends up here. And as it turns out, we can slide the vectors around without changing their magnitudes or their directions, so they're equivalent vectors. So, 100 kilometers east is 100 kilometers east regardless of your starting point. We can talk about positions of things, and then it's a little bit different, but for any of the quantities we're going to do, we can move vectors around without any problem whatsoever. There's another rule about adding vectors, and that they're always added head to tail. So you'll notice that when we drew the first one, and I'm just going to take that off so we can see it a little clearer again as I draw it in. If I'm starting down here and I say, okay, I'm going to go north first, that's the tail down there, and this is the head of the vector. It's basically the arrow portion. The next vector continues from where we left off, so we walked north and then we walked east. So here we have the head of a vector, and it goes to the tail of the next vector. and we always add head to tail. The reason I say that is because I have students all the time who will say, okay, this is my starting position, and I'm going to go north and then east, and that means that I went this direction. And that is very, very wrong for several reasons. But most of them is you can't walk north and then walk east, but back from your starting position again. You have to kind of continue where you left off. So don't do that. Don't do that at all. Basically continue each portion, each vector from where the last one left off. Same idea here. We'll start off at the tail of one vector, and then we go to the head. And then from the head, we'll go to the next tail and up to its head. And then it gives us the overall vector that takes us a little bit northeast. All right. Let's see if we can draw the resultant vectors from these 4 pictures there. We've got vector A, which is going east. Let me just put a little cardinal direction thing on here for those who aren't as comfortable with it yet. We have the first vector going east. The second vector is going northeast. I should say northeast is a little bit of a slang term. It should be north a certain number of degrees to the east, but this one's not labeled, so we'll just say it's roughly northeast. C is going northwest, and D is going southwest, roughly. So if we want to add these, usually before you start adding vectors pictorially, before you draw the arrows, you should think about what it's going to look like. So in this case, A plus B is going to take us east and then northeast. The reason I say that is because don't follow what I'm about to do here, but I'll have a bunch of students that'll go, okay, so it's this plus that, and then my vector's this, and then it goes through the question or off the page, and it makes a huge mess. So if I think about what this looks like before I draw it, I know it's going to go east and then northeast, so I might start drawing it down here and saying there's A, and then B looks like this. And then my resultant vector started in this corner, ended up here, so that's actually A plus B. All right, then we're going to repeat. A plus C, now this one again is going to go east, but then it's going to go northwest, so it's going to do something like this. I'm trying to do it so that it's the same length as A up here, but again, we're just kind of doing a rough estimate, so if it's not, it's not. And then the second one is going to go something like that. Again, I'm trying to do this one. I don't know if I'm getting the length or the direction precisely right, but as long as it's approximate, I think we're in good shape. Okay, so this was A. This is C. The addition of the two, A plus C, started here and ended up there. So this is A plus C. A plus D. Now D is going southwest, so this one I got to kind of start a little higher because I know I'm going to go down from there. So there's my A. And then D goes something like this, give or take. And so I started there, ended there, and that's going to be A plus D. Now, by the way, in some cases, this one's not a perfect example of it, but I think you'll get the idea. If you draw these slightly wrong lengths, I think you could see that A plus D could end up going southwest instead of southeast, depending on, maybe I made my A a little too short or my D a little too long. But either way, it's just a pictorial diagram to kind of tell us what's going on. When we're getting to questions where we're looking for numeric answers, they're going to kind of appear even if our diagram is a little bit incorrect. The diagram is just a tool to help us calculate stuff. We're not going to worry too much about the details in it. Okay, for part D, we're adding B plus C. So again, I'm going to start pretty low here because B is going to do something like that. And C is going to do something like this. And to me, that looks like it's going north and west. B plus D. This one's going to get a little bit weird. I'm going to start down here because I'm going to go up like that for B. and then back down like this for D. And so I think from our starting position, we're going to head northwest. And then finally, C plus D. C looks something like this. D looks something like this. Our starting position is here and our ending position's there. And I'll be honest, I'm not sure that it's actually, whether it's exactly west or if it's a little bit north of west or a little bit south of west. The way I drew it, I think it's a little south. But again, we may be a little bit off on these arrows. So when we go to do the numbers later, we may find out that we're slightly wrong about our directions. And that's okay. It'll all come out in the math. Okay, so that's the gist of adding vectors pictorially when we're just trying to draw what they look like. Nothing too difficult as long as we follow the head to tail. And then remember that our resultant vector, in this case all the red ones, are ones that start at the starting point, and the head or the tip of the arrow ends at the ending point. Now, if vectors are parallel, they're much easier to work with than the ones that we just did. So it turns out that if we're dealing with parallel vectors, directions don't really do much of anything. They just act exactly the same way that scalars do with positive and negative amounts. So in this case, if we think of this A vector as being, here's a perfect example of me being really, really bad with my scales. I think I actually reversed these two, but we'll pretend I didn't. This one says you're heading 3 meters to the east, and this one says you're heading 8 more meters to the east. So in total, you're doing this. And if they're both in the same direction, we can just do A plus B equals 3 meters east plus 8 meters east is 11 meters east. And if the two vectors happen to be in opposite directions to each other, they're still parallel, but heading in opposite directions. This is a lot like taking a number and then adding a negative. So instead of subtracting a value, what we're really doing is adding a negative, and we're saying our first vector went 14 east, and then we came back 5 west. So the difference is here. We're starting here, ending down there. And the length of that vector is going to be 14 minus 5 is 9. So C plus D is 9 meters. And overall, we're still starting and moving to the east. So that's our direction. So adding parallel vectors is really the same as adding and subtracting scalars, except we're always going to be pretty much adding vectors. All we do is we take into account that some of them are in the backwards or opposite direction. And then we kind of do subtraction like we're adding a negative number. All right, so let's just try a couple of these and see if we can do these in our heads. The first one, I've got 4 vectors there listed, E, F, G, and H. So E plus F would be 9 meters north plus 5 meters north. Those are in the same direction. So if I go 9 meters north and another 5 meters north, that's a grand total of 14 meters north. Now, if I go 9 meters north plus 7 meters south, well, if I walked 5 meters north and then 7 meters south, I'd be 2 meters north of where I was originally. So it's really 9 minus 7. We're treating 7 meters south as the same thing as minus 7 meters north. So 9 meters north plus minus 7 meters north would be 2 meters north. E plus H, 9 north plus 4 south is 5 north. F and G, 5 north plus 7 south is actually 2 to the south. F and H would be 5 meters north plus 4 meters south. That's 1 meter north. And G plus H, 7 meters south plus 4 more meters south would be a total of 11 meters south. All right, and that's about it for the basics of how vectors work. So all in all, what you needed to get out of this lesson is the idea of what a vector is, which is just an arrow with a magnitude and direction. Some of the notation specifically for how to define directions. And like I said, we'll stay with northeast, south, and west as opposed to those other fancier things. And then the idea of how to add vectors tip to tail and linear vectors or collinear vectors, parallel vectors, which basically just says treat them like they're regular scalars and just do addition and subtraction. Addition if they're in the same direction, subtraction if they're in opposite directions. Try the practice problems down here at the bottom. If you're getting them, you'll be in good shape. You're ready to move on. And if you're having some struggles with them, let me know and I'll do my best to help you out. Until the next lesson.